Hello, in this lecture we'll answer on two questions. In the first question, we find out the area of this circle, and in the second question, we find out the area of this trapezoid ABCD. So we'll start with the first question. So in the drawing we have a circle, and this is the common standpoint point P. For this common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. In addition, we have also the right angle ACP. This is angle ACP, that is a right angle. We know that sine CP of right angle ACP equals to 4 units in Islam. This is line 7BC, that equals to 1 unit. Again, our mission is to find out the area of this circle. So first of all, we can implement here rule 2. So I'll repeat quickly on rule 2. According to rule 2, the length of two tangents from a common standpoint to a circle are equal. So in the drawing we have a circle, and this is the common standpoint point P. From this common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. In our drawing, we have the common standpoint point P, and from this common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. So I write it down. PA equals to PB according to rule 2. But it is given as the question that PB in total equals to 4 plus 1, that is 5. So PB equals to 5. I write it down, PB equals to 5. And from this equation, PA equals to PB equals to 5. We will derive that PA is also equal to 5 units in its length. PA equals to 5. This side PA is equal to 5 units in its length. In the next step, I'll copy the right triangle ACP in a new page, and we'll implement the Pythagoras theorem on this right triangle, triangle ACP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse is equal to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle ACP that according to the original drawing, according to the Pythagoras theorem, in this right triangle ACP, AP squared, that is the square of the hypotenuse, is equal to AC squared plus CP squared. So I write it down. AP squared, that is the square of the hypotenuse, is equal to AC squared plus CP square. AP is 5, therefore AP square is 5 squared, that is 25. And it is equals to AC square. AC is the missing side, so we write as it is. It is AC square plus CP square. CP is 4, therefore CP square is 4 squared, that is 16. So in total we should find out that 25 equals to AC square plus 16. Here we subtract 16 from this equation and we get that AC square is equal to 25 minus 16 is 9. So AC square equals to 9. Here we'll take a root out of this equation and finally get that AC equals to the square root of 9, that is 3. So here AC equals to 3 units in its length. This is side AC, that is equal to 3 units in its length. So I write it down, AC equals to 3. In the next step, we'll define the center of this circle. This point is point O, and we'll also define the radius of this circle as x. In the next step, we'll join points O and B together by a straight line. OB is of course the radius of this circle, that is equal to x according to our definition. So here we can implement rule 1. I repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and this is tangent AB, that is tangent to this circle at this point, point M. Point M is the point of tendency of tangent AB with this circle. And we also have the radius OM, that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius OB that is equal to x. The radius OB is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. It is given us the question that PB is a tangent to this circle at point B. So PB is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line PB at this point, point C, so here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So each angle we have at the upper side of PB at point C, we have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will make a construction. That is to say, from this point, point O, that is the center of this circle, we will draw perpendicular on AC. Okay, again, from point O, we will go perpendicular on AC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point E. By doing this construction, we can do quadrilateral OECB. Inside quadrilateral OECB, we have 1, 2, 3 right angles. The sum of three right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OECB we have four right angles. And according to rule 5, any quadrilateral that has four right angles must be this rectangle if not a square. So we relate to quadrilateral OECB as a rectangle because it has four right angles. So write it down. This is quadrilateral OEBC, that is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle OECB, side OE must be equal to the opposite side CB. But CB is 1, therefore OE must be also equal to 1. Likewise, according to the sum rule, in the same rectangle OECB, side OB must be equal to the opposite side CE. But OB is x, therefore CE must be also equal to x. What is the length of the missing line segment AE? From the drawing it is very easy to see that AE in total equals to AC minus CC. Again, AC minus CC equals to AE. So write it down. AE equals to AC minus AC. So AE equals to AC, that is 3, minus EC. EC is x. So in total, AE equals to 3 minus x units in its length. A equals to 3 minus x. In the next step, we will join points O and A together by a straight line. OA is of course the radius of OA is the radius of the circle, is equals to x according to our definition. In the next step, I'll copy the right green triangle OAE in a new page and we will implement the Pythagoras theorem on this right green triangle OAE. Here by PT is the progression for Pythagoras theorem. So actually, this is the right green triangle OAE that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle OAE, OA squared, that is the square of the hypotenuse, is equal to AE squared plus OE squared. So I write it down. OA squared, that is the square of the hypotenuse, is equal to AE squared plus OE squared. OA is x, therefore OA squared is x squared, and it is equal to AE squared. AE is 3 minus x, therefore AE squared is 3 minus x squared, plus OE squared. OE is 1, therefore OE squared is 1 squared, that is 1. So in total actually, found out that x squared equals to 3 minus x squared plus 1. Here we'll open the brackets on this side of the equation and we get that x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared minus 2 times 3 times x, that is minus 6x plus 1. So here we have x squared on both sides of the equation, so x squared we get cancelled. Also we cancel x squared in the side of the equation, we left with nothing, that is to say 0. On the other side of the equation we have 9 plus 1, that is 10, or 6x. So here we add 6x to this equation, and we get that 6x equals to 10. So here we divide this equation by 2. And we get that 6x over 2 is 3x, and it is equals to 10 over 2 is 5. So in total we found out that 3x equals to 5. Here we divide this equation by 3, and finally we get that x equals to 5 over 3 units in its length. So actually we found out that the radius x of this circle is equal to 5 over 3 units. Our mission is to find out the area of this circle. Actually, the area of any circle equals to pi times the radius. The area of any circle is equal to pi times the radius of the circle squared. So write it down. The area of any circle is equal to pi times the radius of the circle squared. And therefore the area of our circle will be equal to pi times the radius of our circle squared. The radius of our circle is x, therefore the radius squared is x squared. So in total we found out that the radius of our circle is equal to pi x squared. So it is pi times x squared. X is 5 over 3, therefore x squared is 5 over 3 squared. So in total we found out the area of the circle is equal to pi times 5 over 3 squared. That is to say it is pi times 5 over 3 squared. 5 over 3 squared is 5 squared, that is 25, over 3 squared, that is 9. So in total we found out that the area of this circle is equal to either 25 pi over 9 square units, or in terms of numbers, the area of this circle is equal to 8.727 square units. 8.727 square units. I'll repeat again. We should find out the area of this circle, that is the area that we are looking for in this question, is equal to either 25 pi over 9 square units, or in terms of numbers, the area of this circle is equal to 8.727 square units. So finish with the first question. In the next step, I will present you the second question and we will solve it. So, our mission in the second question is to find out the area of this trapezoid ABCD. It is given us the question that AB equals to 16, AD equals to 17, BC equals to 25, and side DC of trapezoid ABCD is equal to 44 units in its length. Again, our mission is to find out the area of this trapezoid ABCD. Actually, the area of any trapezoid is equal to the sum of its two parallel bases times the height over 2. Therefore, the area of this trapezoid ABCD must be equal to the sum of its two parallel bases. The two parallel bases are AB and DC. So the area of this trapezoid ABCD must be equal to AB plus DC, that is the sum of its two parallel bases, times the height over 2. So write it down. The area of trapezoid ABCD is equal to the sum of its two parallel bases, that is actually AB plus DC, times the height. We define the height as h divided by 2. The height h must create 90 degrees with the two parallel bases AB and DC. So in total, the area of trapezoid ABCD equals to AB plus DC times the height divided by 2. In order to find out the area of this trapezoid ABCD, we'll do a construction. That is to say, from this point A, we will draw a perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and DC. This point is point E. We will define the length. We define the length of this line segment DE as x. And we will define the length of this side AE or line segment AE is h. AE that is equal to h is one side of the right triangle ADE, but AE that is equal to h is also the height of this trapezoid ABCD. Why AE that is equal to h is the height of this trapezoid ABCD? Because of the fact that AE that is equal to h creates 90 degrees with the base DC. So AE is also the height of this trapezoid ABCD. In the next step, copy the right triangle AED in a new page and we'll implement the Pythagoras theorem on this right triangle AED. So actually, this is the right triangle AED that is coming from the original drawing. According to the Pythagoras theorem, in this right triangle AED, AD squared, that is the square of the hypotenuse, is equal to AE squared plus DE squared. So I write it down. This will be equation 1. AD squared, that is the square of the hypotenuse, is equal to AE squared plus DE squared. AD is 17, therefore AD squared is 17 squared, that is 289. And it is equal to AE squared. AE is h, therefore AE squared is h squared plus DE squared. DE is x, therefore DE squared is x squared. So in total we found out that according to equation 1, h squared plus x squared equals to 289. In the next step, we will do another construction. That is to say, from this point B, we will draw perpendicular on DC. actually this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and DC. This point is point F. We know that AB is parallel to DC. So those two angles are both located between the parallel lines AB and DC, and therefore they are defined as an interior angles. In addition, those two angles, the same two angles, they are both located on the right side of the straight line AE, and therefore they are also defined as one-sided angles. So in total, those two angles are both defined as one-sided interior angles. And again, both those two angles are both defined as one-sided interior angles. And according to rule 16, the sum of two one-sided interior angles is equal to 180 degrees. So I repeat quickly on rule 16. In the drawing, according to rule 16, the sum of one-sided interior angles is equal to 180 degrees. So in the drawing, we have line A that is parallel to line B, and line I cuts the two parallel lines A and B. So those two angles, they are both defined as one-sided interior angles. So that is to say, angle 4 and angle 5 are defined as one-sided interior angles. And according to this rule 16, the sum of those two angles is equal to 180 degrees. So angle 4 plus angle 5 equals to 180 degrees. Here, angle 4 plus angle 5 is equal to 180 degrees according to this rule 16. Likewise, we have those two angles that are 3 and 6. They are both defined as one-sided interior angles, and therefore, according to this rule 16, the sum of those two angles is equal to 300 to 180 degrees. Here, angle 3 plus angle 6 is equal to 180 degrees. So we can actually implement rule 16 in our drawing. Why? Because in our drawing, those two, so as I already explained you, those two angles, they are both defined as one-sided interior angles. Therefore, according to rule 16, the sum of those two angles is equal to 180 degrees. So this is the missing angle BAE plus this angle that is the right angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 16. So I write it down. This is the missing angle BAE plus this angle that is the right angle. In total, they must be equal to 180 degrees according to rule 16. Repeat again. The missing angle BAE plus the right angle, in total they must be equal to 180 degrees because of the fact that those two angles, they are both defined as one-sided interior angles, and according to rule 16, the sum of two one-sided interior angles is equal to 180 degrees. So here we will subtract 90 degrees from this equation, and we get that the size of the missing angle BAE is equal to 180 degrees minus 90 degrees is 90 degrees. Okay, this is the missing angle BAE that is equal to 90 degrees in its size, according to rule 16 of course. So actually in quadrilateral ABFE, this quadrilateral ABFE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this four pieces again must be equal to 90 degrees in its size. So inside quadrilateral ABFE we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be its right angle plus a square. So let's do this quadrilateral ABFE is right angle because it has 4 right angles. So this quadrilateral ABFE is right angle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle ABFE, side AB equals to the opposite side FE. But AB 16, therefore FE must be also equal to 16 units in its length. Likewise, according to the same rule, in the same rectangle ABFE, side AE must be equal to the opposite side FB. But A is H, therefore FB must be also equal to H. What is the length of the missing line segment FC? From the drawing, it is very easy to see that FC in total equals to DC minus DE minus EF. Again, FC in total equals to DC minus DE minus FE. So I write it down. FC equals to DC minus DE minus EF. So FC in total equals to DC, that is 44, minus DE, that is X, minus EF, that is 16. So in total, FC equals to 44 minus 16 is 28 minus X. So FC equals to 28 minus X units in its length. In the next step, I'll copy the right triangle BFC in a new page, and we'll implement the Pythagoras theorem on this right triangle, triangle BFC. So actually, this is the right triangle BFC that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle BFC, BC squared, that is the square of the hypotenuse, is equal to BF squared plus FC squared. So I write it down. This will be equation 2. BC squared, that is the square of the hypotenuse, is equal to BF squared plus FC squared. BC is 25, therefore BC squared is 25 squared, that is 625, and it is equals to BF squared. BF is H, therefore BF squared is H squared plus FC squared. FC is 28 minus X, therefore FC squared is 28 minus X squared. So in total we shall find out that according to equation 2, 625 equals to H squared plus 28 minus x squared. Here we'll open the brackets on this side of this equation, equation 2, and we get that 625 is equal to 8 squared plus 28 minus x squared. 28 minus x squared is equal to 28 squared, that is 874 plus x squared minus 2 times 28 times x is minus 56x. So here we subtract 625 from this equation, equation 2. So on this side of the equation we left with nothing, that is to say 0, and it is equal to, on the other side of the equation we have 8 squared plus x squared minus 56x, and 874 minus 625 is 159. So in total we found out that according to equation 2, 0 equals to 8 squared plus x squared minus 56x plus 159. So here we add 56x to this equation, equation 2, and we get that 0 plus 56x is 56x, and it is equal to 8 squared plus x squared plus 159. According to equation 1, we have already found out that 8 squared plus x squared equals to 289. Therefore, we can substitute 8 squared plus x squared in this equation, equation 2, by 289 from equation 1. We will do it now. We get that according to this equation, equation 2, 56x is equal to 8 squared plus x squared is 289 plus 159. So in total we should find out that according to equation 2, 56x is equal to 289 plus 159 is 448. So in total we should find out that according to this equation, equation 2, 56x equals to 448. Here we'll divide this equation, equation 2 by 56, and finally we get that x is equal to 448 over 56. 448 over 56 is 8. So in total we should find out that x equals to 8 units in its length. So we return to the first question and to the first equation. According to equation 1, 8 squared plus x squared is equal to 289. We just right now found out that according to equation 2, x equals to 8. If x equals to 8, it means that x squared must be equal to 8 squared, that is 64. Therefore, we substitute x squared in this equation, equation 1 by 64. We do it now, and we get that according to this equation, equation 1, 8 squared plus x squared, that is 64, is equal to 289. So here we subtract 64 from this equation, equation 1, and finally get that 8 squared, according to equation 1, 8 squared equals to 289 minus 64 is 225. So in total we found out that according to equation 1, 8 squared equals to 225. Here we take a root out of this equation, equation 1, and finally get that h is equal to the square root of 225, and the square root of 225 is 15. So we found out that the height of this trapezoid ABCD, the height h, is equal to 15 units. Our mission is to find out the area of this trapezoid ABCD. We have already found out that the area of trapezoid ABCD is equal to the sum of its two parallel bases, that is actually AB plus BC times the height, that is h, over 2. So the area of trapezoid ABCD is equal to AB, that is 16, plus DC, that is 44, times the height h. We just right now found out that h equals to 15, so it is 15 divided by 2. So in total, the area of trapezoid ABCD equals to 16 plus 44. 16 plus 44 is 60. So in total, this expression equals to 60 times 15 over 2. 60 over 2 is 30, so in total, this expression equals to 30 times 15. So if we found out that, and 30 times 15 is 450. So if we found out that the area of trapezoid ABCD is equal to 450 square units. And again, if we found out the area of this trapezoid ABCD is equal to 450 square units. So finish with the second question. In the next step, I'll summarize the lecture. We'll start with the first question, of course. The first question, our mission is to find out the area of this circle. So in the drawing we have a circle, and this is the common extent point P. From this common extent point P, we have two tangents to this circle, tangent PA and tangent PB. In addition, we have also the right triangle ACP. The right triangle ACP cuts the circle at 2 points, point A and this point. Also note, this is an angle ACP, that is a right angle. In addition, we know that side CP of the right triangle ACP equals to 4 units in there. This is line 7 BC, that is equal to 1 unit. Again, our mission is to find out the area of this circle. So first of all, we implemented rule 2 in the drawing. If we focus on this common extent point P, from this common extent point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. So if we found out that according to rule 2, PA equals to PB. But it is given as the question that PB in total equals to 4 plus 1, that is 5. So PB equals to 5. We can write here that PB equals to 5, and from this equation PA equals to PB equals to 5. We will derive that PA is also equal to 5 units in its length. This is PA that is equal to 5 units in its length. In the next step, we define the center of the circle. This point is point O, and also define the radius of the circle as x. And then we actually join points O and B together by straight line. OB is of course the radius of this circle, that is equal to x according to our definition. Here we can implement rule 1. Why? Because we have the radius OB that is equal to x. The radius OB is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. It is given us the question that PB is a tangent to this circle point B. So PB is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line PB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of PB at point C? We have this angle that is right angle according to what is given in the question, plus this missing angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. The next step, we did the construction, that is to say from this point O, that is the center of this circle, we drew perpendicular on AC. Again, from point O, we draw perpendicular on AC. So actually this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point E. By doing this construction, we created quadrilateral OECB. Inside quadrilateral OECB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OECB, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle plus a square. So we relate to quadrilateral OECB, it's a rectangle because it has 4 right angles. Here, quadrilateral OECB is a rectangle. But we also know that the opposite sides of the rectangle are equal to each other. So rectangle OECB, side OE must be equal to the opposite side CB. But CB is 1, therefore OE must be also equal to 1. Likewise, according to the sum rule, in the same rectangle OECB, side OB must be equal to the opposite side EC. But OB is x, therefore EC must be also equal to x units in its length. What is the length of line 7, the missing line 7, line 7 AE? From the drawing, it is very easy to see that AE in total equals to AC minus EC. Again, A equals to AC minus EC. So A equals to AC, that is 3, minus EC, that is x. So in total, A equals to 3 minus x units in its length. In the next step, we join points O and A together by straight line. OA is, of course, the radius of this circle, that is equal to x. In the next step, I copied the right green triangle OAE. In the equation, we implemented the Pythagoras theorem of this green right triangle OAE. But before that, actually, we already found out that AP equals to 5, CP equals to 4. So in the right triangle ACP, we implemented the Pythagoras theorem, and according to the Pythagoras theorem, the missing side AC equals to 4 units in its length. Again, in the right triangle ACP, according to the Pythagoras theorem, this missing side AC equals to 3 units in its length. So, actually we implemented the Pythagoras theorem on the right triangle OAE. This is the right triangle OAE that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle OAE, A all square, that is the square of the hypotenuse, is equal to AE square plus OE square. AO is x, therefore AO square is x square, and it is equal to AE square. AE is 3 minus x, therefore AE square is 3 minus x square, plus OE square. OE is 1, therefore OE square is 1 square, that is 1. So in total, we found out that x square equals to 3 minus x square plus 1. So here we open the brackets on this side of the equation and finally found out that x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared minus 2 times 3 times x, that is minus 6x plus 1. Here we have x squared on both sides of the equation, so x squared will get cancelled. After we cancel x squared in this side of the equation, we left with nothing, that is to say 0. On the other side of the equation, we have 9 plus 1, that is 10. So in total, on the other side of the equation, we have 10 minus 6x. So 0 equals to 10 minus 6x. Here we added 6x to this equation and finally found out that 6x equals to 10. So here we divided this equation by 2 and finally found out that 6x over 2 is 3x and it is equals to 10 over 2 is 5. So in total we found out that 3x equals to 5. We divided this equation by 3 and finally found out that x equals to 5 over 3 units in its length. So we found out that the radius x of this circle is equal to 5 over 3 units. Our mission is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. So again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle, that is x squared. So it is pi x squared. X is 5 over 3, therefore x squared is 5 over 3 squared. So in total, if we found out, the area of our circle is equal to pi times 5 over 3 squared. So it is pi, and 5 over 3 squared is 5 squared, that is 25, over 3 squared, that is 9. So in total, if we found out the area of the circle, that is the area that we are looking for in this question, it is equal to either 25 pi over 9 square units. So in terms of numbers, the area of the circle is equal to 8.727 square units. So to finish with the first question, the next step actually presented to you the second question, then we solve the second question. Our mission in the second question is to find out the area of this trapezoid ABCD. It is given us the question that AB equals to 16, AD equals to 17, BC equals to 25, and side DC of this trapezoid ABCD is equal to 44 units in its length. Again, our mission is to find out the area of this trapezoid ABCD. Actually, we know that the area of any trapezoid is equal to the sum of its two parallel bases times the height over 2. Therefore, the area of this trapezoid ABCD must be equal to the sum of its two parallel bases. The two parallel bases are AB and DC. So it is AB plus DC times the height. We define the height as h divided by 2. In total, if we found out that the area of trapezoid ABCD equals to the sum of its two parallel bases, that is to say AB plus DC, times the height, that is h, divided by 2. The height h must create 90 degrees with the two parallel bases A, B, and DC. Okay, so in total, the area of trapezoid ABCD equals to AB plus DC times the height h over 2. In order to find out the area of this trapezoid ABCD, we did a construction. That is to say, from this point A, we draw perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and DE. This point is point E. We define the map of this line segment DE as X. We define the map of AE as H. H is also the height of trapezoid ABCD. Why AE is the height of trapezoid ABCD? Because of the fact that AE creates 90 degrees with the base DC. So AE is both the height of trapezoid ABCD, and AE is also one side of the right triangle AED. In the next step, I copied the right triangle AED in the new page and we implemented the Pythagoras theorem on this right triangle AED. Actually, this is the right triangle AED that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle AED, AD squared, that is the square of the hypotenuse, is equal to AE squared plus DE squared. AD is 17, therefore AD squared is 17 squared, that is 289, and it is equal to AE squared. AE is h, therefore E squared is h squared, plus DE squared. DE is x, therefore DE squared is x squared. So in total, we found out that according to equation 1, 289 equals to h squared plus x squared. In the next step, we did another construction. This is to say, from this point B, we draw perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. We define the touching point of the perpendicular from point B in DC. This point is point F. We know that AB is parallel to DC. And those two angles, they are both located between the parallel lines AB and DC, and therefore they are defined as an interior angles. and those two angles are both located on the right side of the straight line AE, and therefore are also defined as one-sided angles. So those two angles are both defined in total one-sided interior angles. So in total, those two angles are both defined as one-sided interior angles, and according to Rule 16, the sum of two one-sided interior angles is equal to 180 degrees. And therefore, the sum of those two angles must be equal to 180 degrees according to Rule 16. This is the missing angle, it is angle BAE, plus this angle that is 90 degrees according to our construction. In total, the sum of those two angles must be equal to 180 degrees according to Rule 16. So repeat again. The missing angle BAE plus the right angle, in total, they must be equal to 180 degrees. Why? Because those two angles, they are both defined one-sided interangles, and therefore according to Rule 16, the sum of two one-sided interangles is equal to 180 degrees. So the sum of those two angles is equal to 180 degrees according to Rule 16. Here we subtract 90 degrees from this equation, and finally found out that the size of the missing angle BAE is equal to 180 degrees minus 90 degrees is 90 degrees. So this is actually the missing angle BAE. Actually, this is the missing angle BAE. This equals to 90 degrees in its size according to Rule 16. So actually, inside quadrangle ABFE, we have 1, 2, 3 right angles. This angle is equal to 90 degrees according to Rule 16. This angle is right angle according to our construction, and this angle is also a right angle according to our construction. So in total, inside quadrangle ABFE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its side. So inside quadrangle ABFE, we have 4 right angles. And according to Rule 5, any quadrangle that has 4 right angles must be its rectangle plus a square. So we have to quadrangle ABFE is a rectangle because it has 4 right angles. Quadrangle ABFE is a rectangle according to Rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So an rectangle ABFE, side AB must be equal to the opposite side FE. But AB is 16, therefore FE must be also equal to 16 units in its length. Likewise, according to the sum rule, in the sum of the rectangle ABFE, side AE must be equal to the opposite side FB. But AE is 8, therefore FE must be also equal to 8 units in its length. What is the length of the missing 97 FC? From the drawing, it is very easy to see that FC in total equals to DC minus DE minus FE. Again, FC in total equals to DC minus DE minus EF. So FC equals to DC, that is 44, minus DE, that is X, minus EF, that is 16. So in total, FC equals to 44 minus 16, 28 minus X. FC equals to 28 minus X. In the next step, we copy the right triangle BFC in the new page, and we implemented the Pythagoras theorem, and this right triangle BFC. Actually, this is the right triangle BFC that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle BFC, BC squared, that is the square of the hypotenuse, is equal to BF squared plus FC squared. Again, BC squared equals to BF squared plus FC squared. BC is 25, therefore BC squared is 25 squared, that is 200. BC squared is 25 squared, that is 625. And it is equal to BF squared. BF is h, therefore BF squared is h squared, plus FC squared. FC is 28 minus x, therefore FC squared is 28 minus x squared. We open the brackets on this side of the equation, equation 2, and finally found out that according to this equation, equation 2, 625 equals to h squared plus 28 minus x squared. 28 minus x squared equals to 28 squared, that is 874, plus x squared minus 2 times 28 minus x, that is minus 56x. Here we subtracted 625 from this equation, equation 2, and finally found out that in this side of the equation we have nothing, that is to say 0. On the other side of the equation we have x squared plus x squared minus 56x, and 874 minus 625 is equal to 159. So in total, according to this equation, equation 2, we actually found out that 0 equals to x squared plus x squared plus 56x plus 159. Here we add 56x to this equation 2 and found out that 56x equals to x squared plus x squared plus 159. According to equation 1, we want to find out that x squared plus x squared equals to 289. Therefore, we can substitute x squared plus x squared in this equation 2 by 289. We did it, and we found out that according to this equation 2, 56x equals to x squared plus x squared is 289 plus 159. 289 plus 159 is 448. So in total, we should found out that according to this equation 2, 56x equals to 448. Here we divided this equation 2 by 56 and finally found out that x equals to 448 over 56 is 8. So we found out that x equals to 8 units in its length. The next step, we return to equation 1. According to equation 1, we have only found out that x squared plus x squared equals to 289. And we just later found out that x equals to 8. If x equals to 8, it means that x squared equals to 8 squared, that is 64. Therefore, we can substitute x squared in this equation by 64. We did it, and we found out that according to this equation 1, x squared plus x squared, that is 64, is equal to 289. Here we subtracted 64 from this equation 1, and we finally found out that x squared equals to 289 minus 64. 289 minus 64 is 225. So we should find out that x squared equals to 225. Here we took a root out of this equation and finally found out that h is equals to the square root of 225. The square root of 225 is 15. So actually found out that the height h of this trapezoid ABCD is equal to 15 units. Again, our mission is to find out the area of this trapezoid ABCD. And I'll explain to you that the area of trapezoid ABCD is equal to AB plus DC, that is the sum of its two parallel bases, times the height, that is h over 2. AB is 16, DC is 44, h is 15 divided by 2. 16 plus 44 is 60, so in total this expression equals to 60 times 15 over 2. 60 over 2 is 30, so in total this expression equals to 30 times 15. 30 times 15 is 450. So in total we should find out that the area of this trapezoid ABCD is equal to 450 square units. Okay, thank you very much.